Good afternoon and welcome to our presentation on PCB material selection for high-speed circuit design. My name is Scott McMorrow. I am a consultant with Teraspeed Consulting, which is a division of Samtec. I've been a consultant for 25 years, have owned my own high-speed design consulting house for 12 years, and recently Samtec bought my company and has expanded the operations to provide consulting to Samtec customers. The subject today is printed circuit board material that's used for high-performance design. And so we're going to go through a little bit of history about printed circuit board materials. Generally, all printed circuit board materials are made with epoxy fiberglass laminates. So the fiberglass is used in the printed circuit boards for strength and rigidity, for structural reasons. And so as a result, that fiberglass affects the properties of the material. So there's a number of different fiberglass types that are used, and they're designated E-glass for electronic glass, which is used in most materials. There's a high silicate structural glass that's generally not used in high-performance electronic, it's not been historically used in electronic systems, but it's now becoming used because of some of its unique properties. And then there's some new glasses, NE glass, S glass, there's a couple of different variants of glasses, which have been specifically engineered to have very low dielectric constant properties. So our glasses, in high-speed design, the reason why fiberglass is an issue and limits our performance or dictates our performance is because of the very high E sub R, the dielectric constant of that glass. So for standard E-glass that's used in most materials, the dielectric constant is 6.6, which is very high. A typical printed circuit board has an E sub R of about 4, 3.5 to 4. So this is very high, and then our NE glass is a bit lower. But what happens is that in a printed circuit board, we have a combination of glass and epoxies. In order to achieve a lower E sub R printed circuit board material property, we have to mix a high dielectric constant glass with a much lower dielectric constant epoxy to generate an average mixture that we're going to be using. That then poses some issues for the electronic properties. So our fiberglass manufacturing actually goes back hundreds of years to fabric manufacturing. Exactly the same technology used to weave fabrics is used to weave fiberglass. And the same terminology is used. So with fiberglass, with any fabric, there are two directions. One is called the grain or the warp direction. That's the direction that comes off of the roll. The other is called the fill or the woof direction. And those are very old, ancient English terms, I think, used in manufacturing fibers. And then in your in the fiberglass, there are a bunch of different categories or styles of weave. And these dictate the number of threads per inch, so how fine the fiberglass is, and then which dictates the actual pitch of the fibers as they're rolled out on the roll. They also dictate the thickness. Some fiberglass has very thick strands of fiber. Other fiberglass has very thin strands of fiber, and those affect electronic performance. So here's an example of three classical fiberglass weaves that are used in electronic products. 1080 glass is, you can see that it has two different fiberglass properties. It has thin fibers in one direction and thick fibers in the other direction. So now you can imagine that if a signal is traveling on a printed circuit board trace on copper, in one direction it'll see one set of electronic properties, dielectric properties. In the other direction it'll see a totally different set of properties. 2116 we'll see is using thicker fibers. and it's a more regular weave. And then finally you see 7628. 7628 is one of the cheapest fiberglasses known to man and woman. It is used in electronics because it's cheap, and it's used for every fiberglass form that's used in construction. It's used in bodies of cars. Any place that fiberglass is used industrially, that is the glass that's used. Unfortunately, you can see the size of the fibers is very huge when compared to the actual size of a 5mm trace, a typical trace on a printed circuit board. So where that trace lands on top of the fiber changes the dielectric and the electronic properties. So because of this, and because of these variations of the fiber weaves, you can see that with the this 106 material, it's a very thin glass. It is 0.033 millimeters thick. It is very, very thin, but you see that there are large holes. Well, in those holes is epoxy, which is very low isobar. Along the fibers, we have a high isobar. So we can see that our material properties, our trace properties, our impedance control changes from region to region to region and direction across this printed circuit board. We have some newer fibers, and I'll call these modern glass weaves, which are known as square weaves. That is, the threads used in each direction are identical, and the pitches, the separation between fibers, is identical. And then what they do is they perform mechanical spreading of the fibers. So rather than a fiber having an oval shape, they, in the manufacturing process, blow a liquid through it or blow air through it under high velocity to spread the fibers out and make them flat. And what you can see is in this direction, the fibers are relatively flat and have flattened out, and the gap between the fiberglass and between one fiber and another has become very small. But in the other direction, it's still fairly wide. Even though it was spread out, it has somehow become unspread, and we'll talk about that. So 1067 is the modern fiberglass weave that's used to replace 106 and gives us much more consistent dielectric properties. Here is 1078, which is another modern weave. It's 40 microns thick. It is, and you can see again the property of the spread weaves. It looks much more flat, but still there are these gaps and spaces. So wherever the color, the density of the color changes, we're going to have a different dielectric property. So there'll be one dielectric constant across here, another going across this way, and yet another going in the other direction. 1080 is a very common fiberglass used in thin printed circuit boards. You can see its irregular weave causes electronic property problems. And the replacement for that is 1086, which again has this square weave and has spread fibers that provide very good coverage of the printed circuit board area. And then finally, this is 1035, which is a very, very thin, 30 micron thick fiberglass. And this is one of the interesting things about fiberglass. Just like any fabric, if you were to take fabric and roll it out on a roll and try to pour a liquid epoxy over it, it would move. And that's known as weave wander. And you can see that in one direction, the fibers are completely parallel, yet in the other they're diagonal. So now you can see that if a trace is running in the warp direction, it has fairly uniform properties, but in the woof direction, or the fill direction, it's crossing those fibers at a diagonal. It turns out that if we look at a statistical sample of a large number of pieces of fabric, that angle can be as much as about 6 or 7 degrees off, which will affect our trace routing and affect our properties of our traces on a printed circuit board. And here's just an example of how we might want to think about how does this fiberglass affect our electronic properties. I think I have a, you can see that in this region there's a crossing of glass fibers, so the density of glass is two times. In this region, the density of glass is 1 times. And so what you can see is, depending upon which direction you go and how our trace is aligned, we will have a different dielectric constant, different properties. This affects trace propagation. It affects the time of flight for a signal, and it affects the skew on different differential pairs. If you can imagine that one side of one trace in a differential pair was running along this 1x glass region, and the other side of the trace was running under the 2x, then we'd have a differential between the dielectric constants, and we would develop skew as the signal propagates down the trace. Now, 2 years ago at DesignCon, Lee Ritchie, who is a colleague of mine and a friend of mine, a fellow consultant, created a paper, did a paper along with Isola, the material manufacturer in the United States. And what they did was to look at different fiberglass and make some measurements. What a silly idea. So took actual fiberglass, the pitch, and they looked at 3313, 1067, 1078, 1086. These are modern glass fiber weaves. And what they found was, in one direction, the pitch was very similar to the average pitch that we'd expect from the way the number of threads per inch in the fiber. But in the other direction, it was different. And it was consistently smaller. Now, I looked at this data and said, I wonder why that is. So if you imagine fiberglass on a roll, it has been spread out, and you roll it out. Just take a piece of fabric and you pull it out. What happens when you pull it in this direction? You put it under tension, and the fibers want to pull in. But in the cross direction, there's nothing to pull them, so they stay in the same alignment. So what we find is that in one direction, the fiberglass pitch is identical to the way it was manufactured. In the other, it's actually shrunk. If you pull fabric out on a table and you put it under tension, it actually shrinks and pulls in. Well, again, that means that the properties in two different directions will be different. We go backwards. It also solves the mystery. So why is this hole here? The hole is there because when we put the fibers under tension, the individual strands in the fiber bunch back up. We spread them out, we put them under tension, and they pull back together. So that is what's creating this variation in properties across the material. Now, if we take these, take some particular materials, all of these are 3313 kind of weaves, and they have a very specific specification. And they were produced on panels with multiple material types. Isola 415, FR 408, Isola iSpeed, which is a new material, Isola iTerra, which is a very new low-loss material, and then several materials with some lower E sub R fiberglass. And they made measurements of a number of differential pairs on multiple boards and looked at the skew. We expect there to be skew because the average dielectric properties between two different traces can be different depending on where they are in the fiber, and we do measure skew. But something interesting happens. We measure fairly low skew on a 9-inch trace in one direction, and we measure fairly large skews, in fact, extraordinarily large skews, up to 123 picoseconds in 14 inches. So in about 14 inches of trace of a differential pair, 123 picoseconds, that's equivalent to reducing or increasing the length of the trace by about, well, 3/4 of an inch, and I don't know what that is in metric. So what we see is the direction that the traces travel on the printed circuit board matter, and it helps for us to know that. And this is not a statistical measurement. This is a measurement of just a few samples. The worst case is actually much worse. So here is a table of all the different fabric styles. And so basically it gives you the designator for the fabric. These are typically used in electronic products, and they're usually available from most laminate manufacturers. Square is an indication of whether the orientation of fibers looks square. They're exactly the same thickness, same weights, and they essentially have the same thread count per inch. Expanded indicates whether the fibers have been expanded in some way. Spread says, have they been spread in some way even further? And then finally, mechanically spread says they've actually used a process to physically spread those fibers out, which is a very reliable process. And what we find is, once we look at all the materials, the new high-performance materials are 1035, 1067, 1078, and 1086. Those are reliably spread. The other one that can be used that is somewhat spread is 3313. So for high-performance designs, those are the fiberglass choices that we have. Now, if you're a design engineer designing a printed circuit board, if you do not specify the fiberglass that's being used, if you don't call that out, then what happens is the fabricator will use whatever they want. And what they want is they're going to use the absolute cheapest material that gives them the most profit margin. So for high-speed, high-performance engineering, we have to actually not just specify the trace width, the dielectric stack-ups, the trace separations for differential pairs, and the dielectric properties, but we also have to specify the actual fiberglass that's being used. So we would call out for example, a 1086 core that is 5 mils thick. Or we would call out a 3313 prepreg in a layer. Now, so why is this important? That we've already shown that we can measure that there's skew in differential pairs. Well, at 10 gigabits per second, if you skew a differential pair, then what happens is that is equivalent to causing mode conversion. That mode conversion causes the differential energy to convert to common mode, or into common mode. Now, common mode likes to radiate all over the place, and it couples into many other things. So whatever gets converted to common mode is lost by the differential pair and turns into insertion loss. So this is a plot of the amount of insertion loss at, in this case, at 5 gigahertz based on different amounts of skew. So for example, that one measurement of 100 picoseconds of skew would have been way, way, way off the chart. It would have rendered the signal totally unusable. At 100 gigabits per second, our eye width is 100 picoseconds. So even if we had a 50 picosecond skew, we would lose 30% of our signal. Minus 3 dB is 30%. We've just lost 30% of the signal. But even at 30 picoseconds, we're losing 1 dB. So it's important to control that skew. However, it gets worse. Because what happens is when we convert to the common mode, that energy is now available to couple and radiate to other things in the system. Now, most traces don't go from many traces don't go from part to part, but they go through connector systems. And those connector systems have vias. Well, connector systems and vias have very poor common mode control, which means when these high-speed signals pass through with this leakage of common mode energy, it bursts and radiates out and causes crosstalk all down the connector array, all down the via array. So this was a case where we did a statistical simulation of an interconnect going through a backplane and connector system, and we increase the skew as we go through that system. And you see that what happens is, in the previous slide at 25 picoseconds, there was only 0.7 dB of attenuation. That's negligible. It's a very, very small amount. However, when we actually run it through the system simulations of the entire model of the system, we lost 38 millivolts. Our eye height has dropped from 60 millivolts to 38. It's an effective 3.9 dB of loss. So what happens is, because we skewed the signal, we no longer attenuated not only attenuated the signal, we ended up spreading that energy out to other places and causing crosstalk. That crosstalk created noise, which additionally closed the eyes of the signals at high speeds. So at 10 gigabits per second, this is important. At 28 gigabits per second, where we're starting to design systems today, it's absolutely crucial to know the materials and control that skew. So here's another example. This is an actual measurement of traces. I showed this in the class earlier today. We basically have multiple differential pairs that have been manufactured on Megtron 6 with 3313 fabric. We know that it's going to cause some skew, and most of the traces we measured had this loss profile. However, there was one outlier. There was one trace out of about 10 that we measured that had 12 picoseconds of skew, and you see what that did to the insertion loss. So Megtron 6 was a low loss material, but as soon as we introduced skew, it's not so low loss anymore. So the skew actually reduced the effective performance of the material. So what we find is we can't just design for the materials, we have to design for low skew in order to effectively use these high-performance, expensive materials to their maximum. So here's a plot of a number of modern materials. What you'll see is, from bottom to top, higher loss materials to low loss materials. So at the bottom is Megtron 4. Just above that is a material called GigaSync. Now, GigaSync is a brand new class of materials created by Isola, which is engineered to be a zero skew material. It is engineered with glass and fiberglass and resin to have exactly the same dielectric constant. So there is, in any direction, it is a flat material that has exactly the same dielectric constant. I've measured it. It's very, very close to being a skew-free material. Now, it's a fairly high loss material. It's about the same as Megtron 4. It has a dielectric loss tangent of about 0.01, and it's good, but it's not a high performance, low loss material. There are a number of other materials, such as this is Isola iSpeed. It's a bit better. It's a new class of materials. This is Megtron 6. This is Isola iTerra and Isola TerraGreen. TerraGreen is a high temperature reflow material designed for the most extreme European and US compliances. And then finally at the top is a new material called Tachyon. And Tachyon is the lowest loss material for manufacturing printed circuit boards and backplanes right now known to man. It is a very, very good material. Now, Except for this green line, the rest of them are not skew free. The rest of them have fiberglass in them. And have fiberglass that isn't controlled E sub R. So there is a new material coming out that is not yet released that will be essentially equivalent to Megtron 6, but it'll have zero skew. It'll be a flat E sub R material. And that's being introduced at the first of the year. It's about all I can say about that. So let me just go back here. So how can we control skew? If we're subject to these materials and they're going to have skew because of the way the fiberglass is oriented, what can we do to control this? Well, the answer is we can be clever. Number one is we can route our traces diagonally. We can either do that by routing them on the board in a diagonal or turning the board so that the traces run diagonally. Now, when we turn the board, we lose space, efficiency on the board, so it costs more. But if we route diagonally, it's hard. It's really hard to make sure that everything runs diagonally. But essentially, if you route diagonally, you sample the weave in both directions and you get a good average. So that's actually a really good technique for controlling skew. And there's some methods where you can zigzag the traces to keep them in one lane. And they affect the same. They have the same effective purpose. The other is another way to control skew is to know what the pitch of your material is, and use geometry to your aid. So here's the pitch of a differential pair. So imagine if our fiberglass. Imagine that our fiberglass is this pitch here, but we routed our traces at half the pitch of the fiberglass. So one trace was on this bundle of fibers and the other was right in the center. I can guarantee you that'll be the absolute worst case performance you'll ever get, because you'll see a huge difference in dielectric constant. But as we move our traces apart so that they align with the center of the fibers and they are designed at the same pitch, they now both see exactly the same dielectric environment. And even if I move them, they're still moving relatively to the fiberglass. And so there'll be a different impedance, there'll be a different propagation velocity, but both sides of the trace will be matched. So even though we don't even though we have to use these fibers and we may not use these these fiberglass matched materials, we can still do a number of things to mitigate this fiberglass weave problem. So we can rotate the traces, rotate the boards, and remember when we do that, it has to be more than 7 degrees because of just the variation in the weave wander. Oh, we can also, if we know that in one direction it's the warp direction, the grain direction coming off the roll, and in the other direction is the fill direction, if we know how the fiber was placed on the laminate panel, we can predominantly route our signals and traces in the direction of the fill fabric, the one that didn't spread out. So that's another option that we have for eliminating skew. None of this totally eliminates skew except the matched dielectric property materials. But it gives us a number of options to essentially increase the bandwidth of our system and increase the reliability of our system. So when we do that, we essentially gain back the bandwidth we lost and the signal integrity we lost, and bring the signals back up to their normal attenuation. So in doing that, we can then use some of these new advanced materials that are easier to process, are higher temperature, that meet all of the ecological requirements, and have extremely high performance. So I'd like to thank you for joining me. And I'd like to open this up to any questions that anybody has. Questions? Yes? So he asked, is it practical or possible to align the fiber, the traces with the fiberglass? And so the answer is yes. Let's say, look at this. I can't guarantee that it's always here, but I can guarantee that relatively they're at the correct pitch. So I know the pitch of the fiberglass. I can design the pitch of my trace. So I can either select a trace pitch center to center or a fiberglass pitch that's matched to my trace center to center differential pair pitch. And by doing so, I guarantee that no matter what position underneath the trace, you see the same dielectric properties for both sides. That's what we care about. Now, that doesn't help impedance control. You'll have lower impedance here or higher impedance there. And if you actually design a test board with lots of traces, you will see it vary from some extreme high point to some extreme low point. So it is possible. And now if you do that and then combine that with some diagonal routing, that does a lot to eliminate as much skew as possible. Because oftentimes when you come out of a device, you have to route parallel. You don't have any choice. So if you can route at the same pitch as the fiber, then you can reduce the amount of skew. And then once you get outside of there, you can route diagonally. Any other questions? All right, well, thank you for joining me. I appreciate it. If you haven't, please register, give us your card. If you need any more information, feel free to ask. And if you fill out a registration form and ask for the presentation, the presentation will be sent to you. So thank you very much.